So when you see a problem like this, and the limit notation says from the left, you have to look at what the value is. It's 4. We're approaching 4 from the left. So that function is attached to the function as we approach it from the left. This function is as we approach it from the right. So if we were looking at this, the limit, there was no notation in the little corner. We would have to check that both of these are the same value. With limits, we don't give a hoot about the one in the middle. We just don't care. What we care about are these two things. So again, if it had no notation there, we would check both values and we would check that they matched. But because of the little notation that tells us we're coming in from the left, we only have to see what is the height as we come into that function to 4 from the left. Well, 4 squared is 16, so we're almost making it to a height of 16. The answer is 16, or A. Yeah, this is what that side of this is what the graph looks like. So if that helps you, we would be at a parabola, open circle, close down here, and then the square root. Okay. Do you have this page on your sheet? Okay, let's take a look at this one. It says that we are going to do all these limits. Let's start with E. It says the equations of the vertical asymptotes. You'll notice I put the vertical asymptotes in green. I think that's on yours. If it is not, put them on there. But let's write, those are always in x equals. So that's x equals -3, x equals 2, and x equals 5. So you always want to contemplate that first. A says what's happening as we approach to an x value of 2. So that's this one. They both match and they're both going down. Our answer is -infinity. This one, we're looking at 5 right here. They're both going up. They both match. The answer is +infinity. This one. This first notation here says that we are just looking at the left side, and it's going to -infinity. Yes, because it's going down. And then this one is going upward from the right, so that one is going up to +infinity. So if they were asking us, what is the limit as x approaches -3, and they did not specify the side, we would say that it is undefined because it's not going up, it's not going down, one side's going up, one side's going down. Remember, limits have to match for both sides to be the same thing for the limit to exist. So this limit does not exist. Any questions on that? And that's just the stuff we went over at the end of 1.5. Okay? Okay. Today we're going to start talking about algebraic ways for us to work with limits. If you're really great at graphing, graphs are going to give us a lot of information. But, you know, when we're dealing with a lot of this stuff, we have to be able to do it algebraically. So we're going to kind of talk about how those things go together and how we can rely on the algebra to verify the graphs or vice versa. Okay. So the limit laws that we want to know, and they're going to feel very instinctual here, but let me kind of highlight what you need to write down. So what the first limit law says, well, first let's look at what they've given us. As we approach C for the f function, we're going to a height of L. As we approach C on the g function, we're going to a height of m. And then this is just a constant. What this is saying is, even if we are taking the limit of the f function and we attach a constant, don't worry about it. Just take the constant and shove it out in front. It will be the constant times that limit. Now let's think about why that happens. if we multiply a function by a value, it is going to change the height to reflect that. So wouldn't it change the height at that particular limit? So it just kind of makes sense. The second part is basically saying that if you have two limits added together, don't worry about it, just split them up and add the individual limits. Same thing for subtraction. If you have two limits subtracting, just subtract them. Multiplying, just multiply them. Dividing, just divide them. But be careful, you can't have a zero denominator. So if the limits work, but if m happens to be 0 at that particular value, you do have to account for that and say it doesn't exist. And then, of course, we can take a power on the outside. And a power on the outside is powerful in the fact that that means that since a square root can be written as a power, square roots are included. So if we know the limit of something is 7, then the square root of that limit is the square root of 7. You don't have to overthink these. I have found that limits are actually pretty easy. You guys want to overthink them and make them harder than they are. So don't overthink. We'll take you through the process, okay? So here are some examples of some of the results of the limit laws we just talked about. The limit of a constant is just going to be the constant. Let's think about a constant. If we have the function f of x equals 7, it's just a horizontal line at 7. What's the limit at any spot along the line? Because it's horizontal, it's always at a height of 7. So the limit's always 7. So that's all that's saying. So no matter what we approach, if there's a constant in there, the answer is just that constant because the limit is always reaching that height. If you have a straight line is always defined if we have especially the nice number x. If we're approaching a, we're going to hit a. So that's great. So if we have the limit as x approaches 2 of x, we're going to hit 2. Here's an example of that same thinking. So remember, we can ignore the power and do it later. We know the limit of that is 5, so then it just becomes 5 cubed. That does say 5 cubed. Same thing here. If we're approaching 5 from x, we can remove that cube root and then just take the cube root of 5. So same thing kind of here. Okay. So those are just rules that happened because of just the logical conclusions of the rules that we saw before. But those are the most common ones. And what you're noticing, hopefully, is that if our function is just either a power function or a nice like polynomial, to find the limit, since it's a continuous function, we're not going to lift our pencil, you can just direct substitute the value in and you're going to get the limit. Now that fails if the value isn't in our domain, if there's a jump, an asymptote, a break of some sort in the graph. So, as long as it's a nice smooth graph like a parabola or a linear function, the limit is the limit is the limit. It's just what's the point value at that function or at that point on the function. So those shouldn't be magical and crazy. They should just be pretty straightforward, okay? Everybody good with the rules that we see here? So those are just examples of how the rule works. So you have a concrete example to look at. So I've just kind of given you one example of how the rule is applied. But as we practice the rules, you'll see they're not so bad. Okay, so now let's look at a function example I wanted you to see that was based upon a graph. You might notice this is happening here and there, okay? So using the limit laws, the first thing I want to get you in the habit of doing for A is let's do all of these, but without looking at the graph. Let's pull them apart, and then we'll go back to the graph. Okay. So our f function is in blue, and our g function is in red. So see how there's a 3 on the f function. So basically, you're just going to take 3 times the limit as x approaches -2 of our f function. Was it f in blue? Yeah. Plus the limit as x approaches -2 of our g function. So all we're doing is we can individualize, take the individual limits. Don't worry about the 3. We can apply it mathematically. You can take a constant and ignore it until the end, and then you go, okay. Now we're not going to get the answer yet on the graph. Let's pull apart the algebra. So this is just the limit as x approaches 1 of our f function times the limit value as x approaches 1 of our g function. So just, you can take each individual limit and then we'll multiply them at the end. So here, what math will we do at the end? Division, right? That's the last thing. So you're going to take the limit as x approaches 3 of our g function. We're going to find that value, and then we're going to divide that by the limit as x approaches 3 of our f function. Okay, so that's algebraically how we're going to rip them apart, so that we can look at the graph and we can individualize and look at each graph individually, and then we'll put the answers back together. Okay, so let's start with part A. So in part A, we are approaching -2. So again, remember how this graph paper is a little wonky. Let's make our x and y axis a little thicker so we can really find that really nicely. But they usually will put a little 0 at the origin. Okay, so -2 is over here. Now the limit is the value we are approaching from both sides. So the f function has a limit of 1. The g function at -2 has a height of -1. So it really just becomes 3 minus 1 or 2. That's as easy as that, okay? Hopefully that made sense. So now for part B, what value are we approaching? We're approaching 1, so we're looking right here. The f function is at a height of 2. The g function is undefined. So we can't multiply those things because one of them works, but one of them is an undefined feature. The reason it's undefined here is we have a jump discontinuity. The word discontinuity is going to give you an idea that we might have an issue with its limit. Now you don't always, but because if it's just a hole there, it's okay. But because this was a jump discontinuity, those piecewise functions can mess that up. So our answer for that one is does not exist or is undefined. And then finally, what value are we approaching for C? 3. So we're going to go over here. Let's assume this hits 3 perfectly. Okay, let's assume they're nice numbers. Okay, so our f function is at a height of 0. Our g function is at a height of Oh, wait, we're opposite. Wait. G is in red. G is at 0. F is actually at 1, 2, 3. No. I'm sorry. I was looking at the wrong point again. Okay. So I'm looking at 3. 1, 2, 3. No, I just can't count. I was going to 2. Oh, okay. So our F function, which is blue, is at 0. Sorry about that. Our G function, which is in red, is at a height of 1. What do we know about dividing by 0? You can't. It is undefined. Does not exist. You can write, again, DNE or does not exist. Okay. Any questions about example 1 using the limit laws from a graph? Okay. Example 2. Now, by the limit laws, now I'm going to do, I'll do these. I don't know why there's extra parentheses and weird stuff. I think I had something different typed at one point. Let's call this one B. Ignore that. It shouldn't be there. I don't know what it's doing. Okay, anyway. What the limit laws allows us to do. Now I'm going to write it out longer, but I'm going to show you what happens. This is really 3 times the limit as x approaches 4 of x squared minus 5 times the limit as x approaches 4 of x plus the limit as x approaches 4 of 7. Now, you're never going to do this ever again. This is a waste of time. But the limit laws allow us to do that. And then let's look at what this means. This portion here, we know the limit as x approaches a number, if you have an x sitting there, is just that number. So what happened? We plugged in a 4. We know this is just the number. We're going to plug in a 4. We know that a limit of a constant is that constant. So look what happened. If we compare it to the original polynomial, it's just something called direct substitution. We can go through the rigmarole of doing the same thing for B. But why? We can use direct substitution as long as it's in the domain. What is the only value that is not in the domain of that rational function? 6. Are we working with 6? So we don't care. We can use direct substitution. So technically, the limit in an algebraic sense, is it in the domain? Do we have an issue? If not, plug it in. But I always tell my students, plug it in at first anyway, see what happens. If you don't get a 0 denominator or maybe a negative under a square root, it's probably, that's what the limit is. So technically, I don't care what the original, A, we could get a number. But B, what are we plugging in? What value can we directly substitute? -2, because -2 is in the domain. It works fine. The top's a parabola, or I mean, well, it is, but top's a polynomial, bottom's a polynomial. Plug it in. So we get -2 squared plus 2 times -2 minus 1, all over 6 minus -2. Now, I know you know how to do that algebra. I'm not going to waste our time doing it, okay? If you wanted to come up with a number, so be it, go for it. But if you don't know how to plug a -2 into a polynomial right now, maybe rethink your choices of sitting in calculus. Just saying, okay? So we're going to leave that as it is, but I hope you know we should get a number, okay? Maybe the number's -1/8, I don't know. But anyway, let's go now to the property that I kind of was pointing toward. If f is a polynomial or a rational function and a is a member of the domain, then just plug it in. Just plug it in. which is an amazing result algebraically. We know how to plug in numbers. Polynomials, every single real number is a member of the domain. So you don't have to worry about a polynomial. You don't have to do any magical thinking for limits of a polynomial. Just plug the sucker in, you get a number, bam, I'm done. As long as you know that rule, it's an easy process. If it happens to be a rational function, so those fractions, like that last one, the only value we can't plug in is 6. Every other one's fine. So rational functions, you know, where's that denominator 0? That's the only thing you can't plug into these. So which makes things great, okay? Now, by the limit laws, we can throw square roots in it, but then you always have to ask yourself, is it a member of the domain? But direct substitution is going to be the first shot in any of these problems you do. Plug it in, see what happens. Now, what this function or what this slide is saying, basically, is if two functions are pretty much the same, except at a point, the limits are going to be the same at that point. Now, how is this helpful? So I'm going to draw for you, in example 4, the function in question, okay? So hopefully you know that this is just the line y equals x plus 1, except at 1, we're going to be at the point 5 instead. Now, think about if I plugged in 1, I should be at the point 2. So that's all this function is. It's a piecewise function with a hole in it, and the hole has been replaced in the wrong spot. So let's draw our g function. So we start at 1, go up 1 over 1, make sure you have a hole at this value right here. And it's really a point up there, but it's just a line. So what this little note is telling us, if I know a function that's acting the same as that, except at the point in question, because limits don't care about the point in question, I can use that instead. So let's call f of x the line x plus 1 that's completely perfect. Would you agree with me that g of x and f of x are the same except for at a point? Yes. So this rule applies. So the limit as x approaches 1 of g of x is exactly the same as the limit as x approaches 1 of f of x. Because they're the same function except at that point, but I don't care. This function, f of x, is a polynomial. What am I allowed to do to polynomials? Direct substitution. So the answer is 2. Now, if I look at g of x, it's hard to see that it's 2. Or you can remember rules of limits say, I don't care what's happening at 1, I care what I'm approaching. If I plug in 1 to this and ignore this, I'm going to 2. So if you use logic, both things will get you to 2. Do you need to find an f of x? Most of the time, no. Sometimes, yes. Here's when. Algebraically, if you try direct substitution and you get some number other than 0 over 0, so 6 over 0, 2 over 0, negative 5 over 0, you found a vertical asymptote. So we have to deal with what's the problem there. But if I get 0 over 0, you have actually just found a hole in the graph, which means the limit exists, but you can't see it yet. So we are going to have to mess with those ones. And I'll show you some tricks about how you mess with those ones when we get to those ones. Any questions? Do we have any questions about 4? Okay. Here's the ones I'm talking about. Okay. So 0 is not in the domain of the first one. 0 is not in the domain of the second one. But you have to discover why. Why is it not in the domain? Is there a hole there or is there a vertical asymptote there? Here's the things to remember. A hole will always show up algebraically as 0 over 0. A vertical asymptote will always show up as some other number over 0. Vertical asymptotes, we got to plug in something close on the left, close on the right. Is it going to positive or negative infinity? So those ones we're going to use a number to plug in. If there's a hole, we have to fix the algebra. And I'm going to show you how. Okay? You should always be able to fix the algebra as long as your algebra skills are, on point. Okay. So, let's take a look at example 5 for a minute. If I see a rational function, I know 0 is not in the domain, but I'm going to wait and I'm going to do direct substitution anyway, okay? So if you plug in 0, so if we try direct substitution, we get 0 plus 4 squared minus 16 over 0. We get 0 over 0. 16 minus 16, 0 over 0. That tells me I got to fix the algebra. I'm going to find some f of x that is equivalent to my original function, but works at 0. Now, there are 3 kinds of functions that we're going to deal with. One is there's some kind of polynomials in each, like this one. It's a nice rational one. And there'll be a way to fix that one. There might be one with square root in it. I'll show you how to fix that one. There might be one where there's a fraction living in the fraction. I'll show you how to fix that one. So there's really kind of 3 types to fix. We're going to look at 2 right now. Okay. So let me show you how to fix the algebra in 5. Expand it out. What's there? We should be able to get rid of that h in the bottom. You might recognize that. That looks very similar to the difference quotient we tried to play with, I think, just at the very end of last year. That is related to that. But anyway, let's take a look, okay? So what is h plus 4? Let's do that math first. Remember, that is h plus 4 times h plus 4, or 8 squared plus 8h plus 16. Now that we know that, hopefully that is something you knew rather quickly. Let's plug it into the correct spot. So we're talking about that has to go right there. Okay, let's plug it where it goes. So you didn't have to do that to the side, but I just kind of wanted to remind you how that works. So that would be h squared plus 8h plus 16 minus 16 over h. At this point, something should be cancelable. Cancelable? There should be opposites. Whatever. We get h squared plus 8h divided by h. If you did it right, the h that's causing the issue in the bottom should cancel out. And so we found that the original function, except for at the point 0, is equivalent to a very simple polynomial h plus 8. So what we found is the limit up here is really equal to the limit as h approaches 0 of h plus 8, which I can use direct substitution for very quickly. What's our answer? It's just 8. I thought maybe that you guys would get that a little quicker, but anyway, there you go. It's just 8. So the beauty of finding an equivalent function, except for at the point we don't care about, is we can just then use direct substitution. So if you get 0 over 0 and it looks like A, for example 5, you have to manipulate the algebra. And usually the way you can manipulate the algebra is if there's a quantity that you can expand it, and things will cancel and be nicer than what you had initially. Okay, now example 6. When I first do this and try direct substitution, I get the square root of 4 minus 2 over 0 equals 0 over 0. Guess what? I got to fix the algebra. That's going to happen. But how do I fix the algebra? So for square roots, to fix the algebra, I have to use the conjugate. So for algebraic expressions like 5, I've got to expand it, see what's really hiding there. For examples like 6, I got to use the conjugate, but that relies on the fact I know what a conjugate is and how to use it. So let me show you what to do. Okay, so let's rewrite the original. We're going to pull out the original function that's sitting in our limit. So I'm going to rewrite this as the square root of t plus 4 minus 2 over t. Okay. The conjugate does nothing but change this sign. That's what the conjugate does. Okay. So the rules of fractions say to find an equivalent fraction, we can multiply the same thing on top and bottom. And that's just what we're doing. So we're going to multiply by the conjugate, the square root of t plus 4 plus 2 on top and bottom. Here's the key, and I can't stress this enough. Actually physically multiply these, but leave these. Because what wants to happen on the bottom is we want this t to go away, because the t is a 0 denominator, which is funky, we don't need. So we want that to go away. So don't multiply those, just leave them. You're going to multiply the conjugates. That's why we put a conjugate there. Okay, now let's talk about how to multiply this. So we already know the bottom, just leave it. 90% of the time, you will leave the bottoms for these problems, especially with dealing with conjugates. Just leave them alone. You are only multiplying the conjugates. You put the conjugate there for that very reason. The conjugates are the difference of squares. Why? Well, a plus b times a minus b is just a squared minus b squared. So this is our a. We get to square it. What's going to happen to the square root? Poof, pops off. This is our b. We're going to square it. What happens? It's just a number. Square it. Don't overthink it. Okay, so if we square that first piece, it's going to pop off. We're going to get t plus 4. When we square the second piece, don't forget it's the subtraction of. So if it's an expression, put it in parentheses. But if it's a number, just put it there. 2 times 2 is 4. Oh my gosh, magic has happened. Something will cancel, the 4s, leaving us with the t. What did we want to happen to the t anyway? What did we want to happen to the t anyway? Cancel out. We don't want that t in our denominator. If it cancels out, you have done your job. In example 5, if the h canceled out, we've done our job. In example 6, if that t cancels out, we've done our job. And if it hasn't canceled out, you made a mistake in your algebra, because it should every time cancel out whatever was causing the issue. So now our equivalent function is 1 over the square root of t plus 4 plus 2. So now we can do the limit as t approaches 0 of our brand new fixed function. It's equivalent to the old, it just doesn't have a hole like the old one does. Do we care about holes in limits? No, we ignore them anyway. So if we can get a function that works, we can algebraically find the limit. We don't need the graph. Think about trying to graph that. What? Maybe if you were Mr. Desmos, you might be able to graph it, but if you're not, no, don't graph it. That's why the algebra is so important. So now we can just plug in 0, direct substitution it. It's a member of the domain, it works perfectly. We get 1 over the square root of 4 plus 2, which is 1/4. Bam, we got it. Now, here's where Desmos can be very important and helpful. Feel free to plug the original into Desmos, make a vertical line and use x's instead of t's, make a vertical line at x equals 0. Where does it almost kind of, if the hole wasn't there, hit the graph? It should be at 1/4. So Desmos and the algebra and the graph should always work together. Do we have any questions about example 5 or 6? You have to know the rule that when I try direct substitution, if I get 0 over 0, I got to fix the algebra. If I try direct substitution, I get a number over 0, I found a vertical asymptote. I cannot stress from now until May that rule you have to know. Excuse me. Everybody good with example 5 and 6? Good? Okay. What time are we living in? I want to see how much we got here. I think now is a good place to stop. Please, these homeworks are not going to be quick. You have a 1-5 and a 1-6 homework due on Sunday. Tonight, you should be looking at a little bit of 1-5. You can start 1-6. Start your homework, and every night is a calculus night. Pick a half hour or 45 minutes or an hour of your time and do some math. You will do much better in this course if you do, and if you spend some time. Feel free, if you want to see me at lunch, I can help you. But you got to do some math, okay?